All right, so today what we're going to do is actually give the proof that we can give recursive definitions on well-ordered sets. And just to kind of remind ourselves about the setup, we're given some well-ordering, and we called it A, and we have some set B, and we have some function from A times P into B. Now, what was this function representing? This was supposed to represent the rule of our recursive definition, where P is representing, it's the set of all the partial functions from A to B. And in practice, as it's gonna turn out, P is supposed to just keep track of all the previously defined values of our recursive function. B is supposed to be representing the output, where all of the outputs of our recursive definition, where those are supposed to be living. So we're given a well-ordering, some set, and some rule, I guess, of a recursive definition. And then what's the result? The result is that then, there's some unique function g from A to B, such that what happens? Such that, well, for any single value, maybe y, in our well-ordered set A, what is going to be the output when we plug in y into G? That's going to be equal to what the rule tells us to do when we have access to y and all the previously defined values. Now, if G is supposed to represent all the possible values, how do we represent all the previously defined values? Well, we're going to take G and then restrict it to the domain where we have only access to the values that are less than y. So the observation here is, well, G is a function, and what we're doing is we're looking at the partial function where we restrict G to the set of all predecessors of y. So this is what the statement of this theorem says. How do we prove this? Well, we kind of alluded to the proof last time, where we're not going to define G all at once, but we're going to prove that we can approximate G. And then kind of magically how it turns out is we take the union of all these approximations, right? A function is a set of ordered pairs, and if they're coherent in some way, if we take the union of all of them, what we're going to get is another function. And magically, this union ends up being the function that we care about. And so I'm going to give a definition that's going to be useful in this theorem of what's called a z-approximation. So this is going to be useful for the rest of the proof, is that for some element z in our well-ordered set A, what we're going to call a z-approximation is essentially a partial answer to this theorem. So a z-approximation is what? Well, is some well, it's going to be some maybe G sub z that is in the domain of it's in P. So it's a partial function from A to B, where we have a few things. Well, the first thing that we want is that the domain of G of z. So maybe we can say the domain of G of z. The domain of G of z is going to be what? That's just going to be all of the values that are less than or equal to z. So all of the values in A that are less than or equal to z. And then the other thing that we want, so what's the idea? It's, well, what if we've given the recursive definition up to and including z? What would have to happen? Well, the domain of this function would be everything that's less than or equal to z. And then the other thing that would have to happen is that this recursive kind of definition, or this recursive bit that we want big G to satisfy, it's going to work for G of z. So in other words, for every single y value that's less than or equal to z, right? Because this is our new domain. So if we consider all the y values not in A, but everything that's less than or equal to z, what would be the case is that if we plug in y into G of z, well, this would be equal to the rule when we have access to y, and we have access to all the previously defined values when we kind of repeated this recursive step all the times before. So we have access to y and also all the previously defined values. So all the previously defined values. Okay, so this is what a z approximation is, just by definition. It's, well, a partial answer to this question. And well, what's the proof going to be? We're going to prove that for every single z in our well-ordered set A. So what's our goal? Whoops. We're going to prove that for every single z in our set A, there's actually a unique z approximation. And this is actually going to be great for us because the what is the big G going to be? It's going to be the union of all of these G sub z's. So then, and we'll kind of mention this again when we get to it, then what's big G going to be? It's going to be the union over all of the z in A of this G sub z. Right? So why does this make sense? Well, if we can do this, then by replacement, the set of all G sub z's would be a set. And so what we could do is take the union of all of these G sub z's, right? We're unioning over all of the z's in A. And by coherence, right? Because all of these are uniquely defined, this thing ends up being a function. So I guess that's another thing that we'd have to check. So how does the proof of this thing go? Actually, what we want to do first, instead of proving that there is something, let's actually prove that there's at most one z approximation. So in other words, if there were two z approximations, they were actually equal to each other. So it's kind of let's maybe start with that. So let's maybe claim one. Let's prove that for every single z, there's at most one z approximation. So for every single z, well, if g sub z and g sub z prime, say, were z approximations, maybe are z approximations, well, then they're actually equal to each other. So then they're equal to each other. Then they're equal. I guess we can just say g sub z is equal to g sub z prime. Okay, so this is what we want to prove first. And well, how do we do this? Well, let's just kind of do it by, we can do this by induction. So what's the proof? What's the proof of this? What's the proof of this claim? So fix some z in A, and let's assume that these things are both z approximations. So what we're going to do is we're going to prove by induction well, what are the domains of both of these things? Well, since they're both z approximations, the domains of them are the same. It's going to be everything that's less than or equal to z. So we're going to prove by induction that for every single y that's less than or equal to g sub z, we're going to prove that g sub z of y is equal to g sub z prime of y. And so how do we prove by induction that something is true for every single y, say less than or equal to something? Well, we're going to affix a y that's less than or equal to z, assume that that statement is true for everything that's less than y, and then argue that it actually had to be true for y. So in other words, towards that end, what we can do is, well, we can fix y that's less than or equal to z, and assume that for all x that's less than y, we have that g sub z of x is equal to g sub z prime of x. And what's our goal? Our goal is to show that, well, g sub z of y is equal to g sub z prime of y. Well, why does this follow? We can just write out the definitions of what a z approximation is. So then, g sub z of y, say, well, by definition, that's going to be what we get when we take the rule and apply it to y, and we have access to all the previously defined information. And so again, what is this right-hand term? This is the partial function that codes all of the previously defined values, right? This is the partial function it's going to be like, say, g g sub z of 0, and then g sub z of 1, and then 2, and then so on. But it's for every single value that's less than y. Well, what are we assuming in our induction hypothesis? Well, if we took any value that's less than y, and we output it g sub z of that value, it's going to be the same thing as g sub z prime of that value. So what this is going to be equal to by the induction hypothesis, this thing is going to be equal to this is going to be equal to big F of y. And then instead of g sub z, it's going to be g sub z prime, where we now have access to we still have access to all the previously defined values. But by definition, what is this equal to? By definition, this is just equal to g sub z prime of y. But that's what we wanted to show, right? We wanted to show that if we had two z approximations, they're the same. So what we did was, well, we argued by induction on every single value less than or equal to z that this was true. And well, this was exactly what we needed to prove in order to get the induction to go through. Well, we fix some y less than or equal to z, assume that it was true for all x less than y. So the statement that we wanted was true for we assumed that the statement was true for all the values x less than y, and we argued that it actually also had to be true for y. So this means that the induction goes through. So what happens here is now we have that for any z in A, we know that there's at most one z approximation. And we're going to actually use this to show that there has to be at least one. So that this is our first claim. And then our next claim is going to be what? Well, our next claim is going to be, we want to prove now for every single element in our set Z that there is at least one. Or we can do something stronger because we have the second claim. We're going to prove for every single Z in A. Now we're going to prove that there's exactly one Z approximation. I'll call this thing G sub Z. And what's the proof of this going to be? It's also going to be by induction. So we're going to prove this by induction. So proof 2. So by induction. So how does this work out by induction? Well, we're going to fix some z in A. So fix z in A. Fix z in A. And, well, what are we going to do? We're going to fix z in A, and we're going to assume for every single y less than z. So assume for every single y less than z that there is a unique z approximation G sub z. So, and assume for all y less than z, there's a unique y approximation, not z approximation. There's a unique y approximation. G sub y. And so what do we need to do now? We need to prove that there is a unique z approximation G sub z. But by claim 1, we actually only need to prove that there is a z approximation. Right? Because by claim 1, we know that if there were two, they had to be equal to each other. So by claim 1, it is enough to show that there is a z approximation. Right? Because then it would have to be unique. All right, so how are we going to do this? The observation is that, well, so maybe an observation is that if we had some, let's say that we were working with values that were just less than z. So if we had maybe some x that was less than y, and we know that this is less than z. Well, we know from, because x and y are both less than z, that there are unique x and y approximations. So if x and y are less than z, then we know that g sub x and g sub y, they exist and are unique. But we can also say that, well, if we took g sub y, right, the bigger approximation, we're kind of approximating more terms in a recursive definition. If we restrict this, so if we consider this function where we restrict it to all the values, maybe less than or equal to x. So maybe we're we're taking this g sub y, this y approximation, and we're restricting the domain of this y approximation to all values that are less than or equal to x. Well, what is this? This thing is going to be an x approximation. So this is an x approximation. It's an x approximation. Right? Well, g sub y is a y approximation, and I guess there's something you have to check. But if we took the y approximation, the bigger approximation of our kind of entire recursive sequence, and we restrict it to all the values less than or equal to x, this is exactly what's going to be true, or this is exactly what an x approximation is going to be. But what do we know? We know by our induction step that, well, this approximation is unique. So what has to be the case is that g sub y restricted to this set is just going to be equal to g sub x. So what can we say? So g sub y restricted to this domain, all the values less than or equal to x, this is just going to be equal to g sub x. All right, so why is this observation interesting for us? Well, it allows us to say that, well, if this is true, if we take smaller values in our kind of well-ordered set and we get kind of, or if we take larger values in our well-ordered sets, what's happening here is that the recursive approximations are extensions of the previously defined approximations. So what's the implication of this? So this implies what? Well, maybe I'll write it like this. This implies for all x which is less than y, and maybe I'll just write it out like this. So this implies that if x is less than y, and I guess is less than z, then what has to be the case is that g sub x is going to be a subset of g sub y. All right, so this is maybe a little bit strange, but g sub x is a function. Functions are sets of ordered pairs. And, well, g sub y is also a set of ordered pairs. What does this mean? This is another way of saying that, well, g sub y, if you restrict it to the domain of x, of g sub x, you get the same function. Well, that's exactly what this statement is. So in other words, g sub y is an extension of g sub x. One of the really nice things is that if we have functions like this, so they're proper extensions, if we take the union of all of these functions, what we get is another function. So this implies that if x is less than y, then we have this claim. In other words, g sub y is an extension of g sub x. So what we get, so it follows that maybe we'll call it g star. This is what, by definition, this is going to be the union of all of the y values less than z, right? Because we haven't defined anything for z yet. But if we take, maybe that kind of looks like a k. Wasn't trying to be. Maybe g star. This is going to be all of the y values less than z. We're going to take the union of all of these things. A union of what? All the g sub y's. We're taking the union of all of these functions, and well, since they're all extensions of the previous ones, this is itself going to be a function. Is a function. So this thing is a function. Okay. Well, why is that cool? Well, what can we say now? We can say that if we took well, we still need to define our z approximation. How can we do this? So what we can do is define well, g sub z is going to be what? Maybe we'll we can give it by cases. Well, either y is going to be less than z. Well, if y is going to be less than z, we'll just make the output whatever g star of y is. So g star of y, if y is less than z. And kind of the case that we didn't know yet is, well, what happens when we want to output z? Because our definition of a z approximation, remember, is everything that's less than or equal to z. So what's g star going to be if we output z? So it's going to be, it's going to be big F of y. And then what? Well, we're going to have access to all the previously defined values. X and a such that x is less than y. Well, if what happens, if if y is equal to z. So in other words, what is this z approximation going to do? Well, it's going to be whatever the same output would have been with our previous approximations if we kind of have a value that's less than z. But if we were equal to z, we're going to output what the rule would do. What we're going to output what the rule would tell us to do if we, I guess, if we were in the case where we cared about what g of z is. So in other words, g sub z of z is going to be what the rule tells us to do when we have z, because y is equal to z, and access to all the previously defined values. Well, by definition, almost. Yeah, maybe you have to kind of check formally to see if it works out, but g sub z, this is a z approximation. And well, by claim 1, it's a z approximation, it has to be unique. So, then g sub z is a z approximation. And is unique. By claim 1. And I guess this is the proof of our second step, of our second claim, right? Because we just argued by induction that if we took some z and we assume that there's a unique y approximation for everything that was less than z, then there's actually also a unique z approximation for z. So there's a unique approximation for z, which we call g sub z. Okay. So what do we do from here? Well, we're almost done. All we need to do now is, well, how do we finish things up? For every single value of z in A, in our well-ordered set A, we now have a unique z approximation, and we get the same type of observation, well, that for every single x and y that are less than each other in our entire well-ordered set, well, the x approximation and the y approximation the y approximation is going to be an extension of the x approximation. And so what's going to be our big G? Our big G is just going to be the union of all of these approximations. So how do we maybe kind of finish things off strong? We can maybe say something like this. Okay. So what do we have access to now? So what can we say? For every single, say, z in A, we have that there's some unique z approximation g sub z. And what we can do now is let's define big G to be the union over all the values in A, so all the z values in A of our z approximation. Well, what we can do is then, maybe I'll kind of leave it as an exercise, but we can check that this actually satisfies the definition. So this works. So in other words, what has to work? Well, maybe the first thing that we'd want to check is, well, g sub y is going to be equal to big F of y, and then we take g, restrict it to the set of all values that are less than or equal to, that are less than y, right? Because we have access to all the previously defined recursive definitions. And well, why does this hold? Well, it's because this is the union of a bunch of things. And for all of these kind of approximations, this statement is true, right? G sub y is going to be, big G of y is going to be equal to g sub y of y, right? And for g sub y, the y approximation, this statement is going to hold. So that's why this first claim is going to hold. And then the other thing I guess that we need to check is that G is unique. Why is G unique? Well, if it wasn't, there'd be some like least value for which it wasn't unique. But then that would imply that that approximation wasn't unique, which would be an issue, right? Because we proved that at each stage there's a unique approximation of this big G. Okay, all right, but then that's the proof of our kind of recursive definition, right? All right, so what we're going to do next time is, what we're going to start working on is we're going to work towards giving a definition of what an ordinal is. It's a certain, an ordinal we can think of as somehow like classifying a well-ordered types of well orderings. And in like set theory, it's probably one of the most, or maybe the most important definition in the field. Maybe I'll mention, I'll just kind of mention something in passing that we go back up to the statement of the results. So here's the thing that we here's our statement that we kind of proved. So one thing that's kind of happening here is that we're giving recursive definitions on sets, and so what kind of has to happen is that this set B, we kind of have to know where all of the recursive outputs are going to be before we give our recursive definition. So in other words, we need to kind of know where all the outputs are going to be. And sometimes what happens is maybe we don't know. It might be tough to figure out where exactly it's going to be. So in the case, I think with the defining the Fibonacci numbers, we knew that all the outputs were we knew that all the outputs had to be natural numbers. But what's going to happen sometimes is we're going to give recursive definitions where we're defining larger and larger like ordinals, say. And well, we would have to know in advance what that set of all ordinals is that's going to that we're going to get from this. Now, there are different versions of the recursive definition for well-ordered sets, and one of them is that allows us to kind of deal with this by maybe doing some type of recursive definition on a class, whatever that means. And I'm just mentioning that this statement is involving just sets. There's some maybe technical issues about getting it to work in specific cases, but this is kind of an introduction to axiomatic set theory. So we're going to maybe be a little bit, we're maybe going to ignore that a little bit, or maybe I'll try to mention it where it comes up. But there are different versions of this that maybe work in situations where this exact theorem might not exactly hold. Okay, but if that didn't make any sense, maybe just forget I said anything. All right. So next time, what we'll do is we'll talk about ordinals.